This is 3.5, complex zeros and the fundamental theorem of algebra. A lot of the stuff we're going to go over in this section will seem redundant of what we did with just real numbers. So we're going to use synthetic division and the quadratic formula to come up with some imaginary numbers. So it just extends it into complex numbers. And just as a refresher, a plus bi, this is your real part of it. So, the earlier sections we were finding real zeros, and now this is all called a complex number. So every number is actually complex. Every number is complex. Sometimes we just deal with the real component of it, but that's it. The synthetic division, the polynomials, finding zeros, all applies for complex numbers. So the fundamental theorem of algebra basically says there exists a polynomial with complex coefficients that has at least one complex zero. So that every polynomial that n is greater than or equal to 1, it has at least one complex zero. So the complete factorization theorem, we kind of covered this with real numbers, but again, it applies to complex numbers. So, and I do want to emphasize, so like if these are the numbers that we have for they're zeros, then this is literally the factors of them. So if we said x equals 5 is a 0, then x minus 5 is the factor. So there's even with complex numbers, you're subtracting. When you minus 5, you get x minus 5 is a 0, and see that's a factor. But it's true with the complex number. So even if I had x equals 5 plus 2i, that is a 0, then x minus 5 plus 2i is a 0. All right, so if that's a 0, then that's also a factor. So just keep that in mind. That's what the complete factorization theorem says. So the zeros, we talked about this earlier with real numbers, and we talked about it. There exists at most, whatever the highest exponent is, at most that amount of zeros. But with complex numbers, the zeros and their multiplicities, you'll see something else happening here. So notice here you have a polynomial with multiplicity of 3 for the x minus 1. So this is x minus 1 equals 0. So the 0 is 1, and it's happening 3 times. Multiplicity of 3. This is negative 2, but multiplicity of 2. And this is the 0 is negative 3, but it's multiplicity of 5. So it's a complete factorization of it, and it has the following zeros with multiplicity. So I just want to remind you about that, and then let's look at the zeros theorem. So for every polynomial of degree n has exactly n zeros. So that's nice to know. So it says find the complete factorization in all 5 zeros. So notice this. Earlier we talked about, because the exponent's 5, it has at most 5 zeros. But here the theorem's actually, it says, whatever the degree is, it has complex zeros of 5. So that literally has 5 complex zeros. It has at most 5 real numbers, but it has 5 complex numbers. So even on this one right here, if you notice, we would have 10, because we have 2 of them, 3 of them, and 5 of them. So we actually have 10 zeros in that problem, and there's going to be 10 complex zeros altogether, if you include the multiplicities. All right, so it says find the complete factorization of this. So if you notice that it has a GCF, so you're going to factor out a 3x. And then once you do that, you're going to get that. I just took the GCF out. Now notice this does factor further. So normally, with quadratics, if we had something like this, you would say x plus 4, x plus 4. But notice it's x to the 4. So this is literally x squared plus 4, x squared plus 4. So I factored it. And notice if I wanted, since I'm trying to find p of x here, and if I wanted to find a 0, so if I set this equal to 0, I can see that this is going to give us 0. If I set this equal to 0, I'm going to get 2i and negative 2i. positive 2i and negative 2i. So remember x squared plus 4 equals 0, x squared equals 4, negative 4, and then you take the square root of both sides. That's how come we get plus or minus 2i. Right? So you're literally going to get those zeros, and notice that's a 0, that's 2 zeros, that's 2 zeros, and that adds up to be 5 zeros. That's what we came up with. So those are 5 possible zeros. And you notice, so if we list the multiplicity, so like positive 2i has a multiplicity of 2, and then negative 2i has a multiplicity of 2, and then 0 just happens one time. So those are all my 5 zeros. All right, so let's look at it from a different perspective. So what if we wanted to find the polynomials with specific zeros? So like letter A, and we probably don't need to do both of these, but it's the same idea. So letter A says find a polynomial of p of x of degree 4 with zeros I, negative I, 2, and negative 2. So if I know these are zeros, again, I is a 0, that means x minus I is a factor. And then negative I is a 0, so x plus I is a factor. 2 is a 0, so x minus 2. And negative 2 is a 0, so I'm going to, the factor is x plus 2. So if I multiplied all of that out, I'm going to get that. Keep in mind, I times I, or I squared is negative 1. So again, if I multiplied all that out, I'm going to get that. Now remember a couple slides ago when I showed you the factor theorem, the complete factorization theorem. Notice this right here. Once I factor it, or get my polynomial, there is an a right there. All right. So what we want to do is find out what number that a represents. So this right here is my polynomial that I'm trying to find. And so notice they give us another piece of information that we need to do. So p of 3 equals 25. So when I substitute 3 in for x, so 3 to the 4th minus 3 times 3 squared minus 4, a, and notice it equals 25. So once I solve this, I'm going to end up getting a equals 1/2 once I solve that, which means the polynomial that I'm trying to find in this problem is 1/2 x to the 4th minus 3x squared minus 4, which is 1/2 x to the 4th minus 3 halves x squared minus 2. So this is my final answer for the polynomial. So this is a loaded problem just because you have to multiply a lot of problems here. First, starting off with multiplying the all 4 of those factors, and then once you get that, you have to use this information right here to find out your a value. To go to do that, to find your polynomial. So this is the polynomial that has zeros, I, negative I, 2, and negative 2, such that p of 3 equals 25. So let's look at another one where it says find a polynomial of p of x of degree 3 that has an integer coefficients of zeros of 1/2 and 3 minus I. So notice something specific about this, because 3 minus I is a 0. Remember we talked about this earlier, last section. If 3 minus I is a 0, that means also 3 plus I is a 0. So now I know 1/2 is a 0. There's 3 zeros. That's why it says degree 3. So x minus 1/2 is a factor. X minus 3 minus I is a factor. And x minus 3 plus I is a factor. Okay, so those are my 3 factors, and it's just a matter of multiplying all of those out. So, what I would do first is I would probably, you don't have to do it this way, but I would use kind of the distributive property, so negative 3 plus I, and use the distributive property here as well, negative 3 minus I, and then you need to multiply all of that out, and we're going to get that polynomial. Now, the only thing that we got to pay attention, go back and read it. It says find a polynomial of degree 3, which we did, but it has to have integer coefficients. And so what we just have to do, notice there is one fraction in there, so we're just going to multiply everything by 2. So so now it becomes 2x cubed minus 13x squared plus 26x minus 10. So now it's a polynomial degree 3, and they have integer coefficients. So that's how you would find that polynomial. So if I had an example here where it says finding all the zeros of a polynomial, we did this last section. You would need to find all the rational possible zeros of this. Remember P divided by Q, find all of your rational zeros for walking through that, which is all of those possible things, possible rational zeros. And then you just start using synthetic division. And you go through the synthetic of guessing which number it is and finding the zeros, and you're going to end up getting x equals 2 as a 0 and x equals negative 1/3 as a 0. Which means, as far as the factors, x minus 2 is a factor and x plus 1/3 is a factor. And again, using synthetic, you'll find out what is remaining is x squared plus x plus 2. And then again, what we're trying to find, it says find all 4 zeros. Again, it's 4th power, so it has 4 zeros. So this does not factor. This thing does not factor. So we're going to have to use the quadratic. And once you get the quadratic for this, you're going to end up getting the other 2 zeros, which is negative 1/2 plus or minus this. Well, let me write the I first, but let me back that up. So the square root of 7 has I. So those are the other 2 zeros. So if I listed all 4 of them, so we already have 2 of them. So x equals negative 1/2 plus the square root of 7 over 2I, and then x equals negative 1/2 minus the square root of 7 has I. And that's all 4 zeros to go to do that. They're all complex. Okay, they're all complex numbers. They're all 4 zeros that we just found. 2 of them are real, and 2 of them are imaginary. So here, if our last example, it just says factor P into linear and irreducible quadratic factors. It's very similar to what we just did. So you're going to list all the possible rational roots for this, and then start using synthetic division to be able to get to your answer. So it's the exact same things what you're going to do. So here you have the polynomial. X to the 4th, and notice that means there's 4 zeros, complex zeros. So 2x squared minus 8. And then when you use synthetic, don't forget about the cube. X cubed is missing, so you're going to have to put a 0 there. But you're going to end up getting factors. If you did this using synthetic, you can do that if you want. But you should also notice if you just always pretend that it's a quadratic. Okay. If it was just a quadratic, a lot of you guys can do it with quadratic, not a problem. So this would be x plus 4, x minus 2. And so this would actually be x squared plus 4, and then x squared minus 2. So you don't have to use synthetic, but if you wanted to stay with the routine, you could use synthetic and you would end up getting that as well. But this right here factors to that, and then what you do need to do is set that to solve those. So if you set those equal to zeros, x squared plus 4 equals 0, you're going to get x squared equals negative 4, and which means x equals plus or minus 2I, and then the same thing with x squared minus 2, set that equal to 0, and you're going to get plus or minus the square root of 2. So notice I have all 4 of my zeros, so there's 2 of them, and there's 2 of them. So my factors, notice what it does, it tells you to factor them. So my factor is x minus 2I, x plus 2I, x minus the square root of 2, and x plus the square root of 2.